Good morning, everyone. Thank you for attending our session, Cloud on Steroids, Accelerating Your Cloud via Cyborg. I hope you can enjoy our session as well as the beautiful sceneries in Vancouver. My name is Jinhua, and my English name is Coco. Next to me is Zheng Hao, and we are both staff researchers in the Novel Research. Today, we are going to talk about 5 sections. At first, we will introduce the background of the acceleration management. And next, we will briefly introduce Cyborg project. And then we will focus on how the Novel use Cyborg in our production to satisfy the real-world requirements. And the fourth part is a demo, and the fifth part is summary. Why I'm responsible for the first 3 sections, and Zheng Hao is responsible for the last 2 sections. Well, the first section is a necessity of acceleration management. In this section, we will take a look at the different kinds of accelerations in cloud and the challenges they may face. You know, as more and more workloads migrate to cloud, the mass concentration of same workloads makes the acceleration management a necessity. And to satisfy the compute performance requirements, there are compute accelerations. For example, the HQs and the multicast offloading may be needed in a virtual broadband access server in the Telco fixed-line networks. And the model training acceleration may be needed in the TensorFlow application. And their next generation firewall acceleration to handle the millions of workflows dynamically greater than 100 Gbps, and their storage acceleration to meet the different kinds of storage performance requirements, like their NVFE Open Fabric enabled acceleration and high performance persistence memory. Also, there are network accelerations like the virtual networking offloading and open vSwitch offloading. And these accelerations can be used in different usage scenarios, such as AI, NFV, the blockchain, big data, genetic sequencing, and these accelerations may be needed in the different cloud architecture layer, like the VM layer or the infrastructure layer. To provide these different kinds of acceleration capabilities, there are different kinds of accelerators, like the software, and the software accelerators is like the DBDK and SPDK, and there's hardware accelerators belongs to different vendors and have different kinds of hardware architecture, like the ASIC, GPU, FPGA, etc. Using these accelerations in cloud, the challenges are obvious. First of all, it's difficult to standardize various technologies, which I mentioned in the last slides. Secondly, accelerators are expected in different contexts and usage scenarios with different forms. Like in NFV, the DBDK, and GPU, FPGA, and QAT may be needed. And in blockchain and machine learning, the GPU and FPGA may be needed. To use these accelerators can be used virtualized, shared by time, and pass-through, etc. At last, it's costly to accelerate. Not only the high price of the hardware, but also the non-trivial management efforts. In Nova, there are some by-hand effort now. When doing the GPU pass-through, users need first to check their PCI address of the hardware, and then configure the whitelist in their Nova configuration. To cope with these problems, we need to we need a unifying net acceleration management framework and to enable acceleration capabilities. And in OpenStack, there are Cyborg project independent of Nova neutral Cinder, and to provide the acceleration as a service. Well, the second section, we will introduce Cyborg project comprehensively, not only the definition and the architecture, but also its interactions with other OpenStack projects in upstream design. The Cyborg was first named Nomad in February 2016, and it had become an official project in last September. In the inquiry release, it has implemented API, DB, conductor agent, and a genetic driver. And in Rocket release, it planned to complete the integration with Nova. And Cyborg is a general management framework for both hardware accelerators and software accelerators, and it aims to provide lifecycle management of accelerators. And the lifecycle management includes but not limited to discovery, program, attach, detach, and remove. As for the Cyborg architecture, Cyborg API and the conductor on the control node, and since it's similar to other official projects, I won't spare time on it. And the Cyborg agent is on the compute node. It's responsible for collecting information for accelerators and reporting it to conductor, as well as managing different accelerators lifecycle via the Cyborg drivers. And for each type of drivers, there are multi-vendor drivers. Next is how Cyborg being used in OpenStack, where according to the Cyborg specification in Rocket release, there are two main use case groups. Hence the interactions are a little different. In the first use case group, accelerators are attached to a VM, where workload demands accelerations. That way, Cyborg interacts with Nova, and examples are like the FPGA and the GPU. The GPU and the QAT. And all Cyborg interact with Nova and glance like FPGA. In the second use case group, accelerators are used by the infrastructure and then utilized via the appropriate service, like accelerating OpenV switch using DBDK, and then utilized via neutral. And for scheduling an instance that needs accelerators, Cyborg needs to work with Nova through three steps. The first one is representation and discovery. In this step, Cyborg should represent the accelerators as resources in their placement. When the device is discovered, Cyborg should update the resource inventories and in placement. And the second one is instance placement and scheduling. In this phrase, Cyborg shall provide a filter or waiter to limit the host based on the available accelerator resources. That way, Nova can select the best host, then passing down that request to a compute node. The third one is attaching accelerators to instance. In this step, Cyborg should define a workflow through a new OSACC library. In that way, Nova Compute can call the OSACC to perform the attach or detach actions. For more details of the OSACC, please keep an eye on the upstream discussions. The third section talks about how Lenovo use Cyborg in our real world and to satisfy our real world requirements in different usage scenarios. In this section, we will briefly introduce our work based on the Cyborg upstream work. Then we will focus on the introduction of Cyborg use case, GPU, and FPGA. In the real world, Lenovo have requirements from different usage scenarios: AI, blockchain, big data, and NFV. Take NFV as an example. There are many workloads which requires high performance and extreme low latency. And to satisfy these requirements, we come up with a Lenovo acceleration solution, which is demonstrated in this picture. We have plenty of accelerators like GPU, FPGA, Natrons Manic, Convenience Manic, Intel QAT, and DBDK. And to manage these accelerators, we use Cyborg to do the lifecycle management and to form a standard workflow in Nova. And as for the Lenovo's efforts on Cyborg, we contributed and will keep contributing to the Cyborg upstream. Also, based on the upstream works, two things have been done in our productions. And first, we implement the Cyborg integration with Nova, where in the upstream, Cyborg is going to interact with Nova placement. And Nova introduced Nova placement in Newton release. And in our solutions, or in our environments, there are still productions before Newton release which don't have the Nova placement. Hence, we modify the scheduling workflow without Nova placement. And if your environment is similar to us, maybe you can refer to our implementation. Besides, we provide the accelerator during VM boot time, or later on via a separate attach and detach actions to dynamically use these accelerators. Second, we implement drivers not limited to the FPGA driver, but added GPU Natron drivers to accelerate different workloads. We will share our work on GPU and FPGA, and for most of the other use cases in our scenarios, the workflows are quite similar. The first is a workflow of GPU attachment at VM boot time. To attach a GPU at VM boot time, Cyborg works in 3 phases. The first one is the resource updating at device discovery. In this workflow, Cyborg agent periodically retrieve the accelerator information like the product ID, vendor ID, and the PCI address, and through the the drivers and update to the CyberDB through the conductor. In the second phrase is triggered by the Nova when doing instance scheduling. In this workflow, users create VMs with specific image properties via the Nova API. In our implementation, it's named the hardware accelerator. Then Nova conductor called the scheduler called scheduler with specific filter. And this filter will call the Cyber API and gather a list of compute nodes which has the GPU resources. The third, so that Nova conductor can decide which node to explore the VM. The third phrase is triggered by Nova in compute node when attaching accelerators to instance. In this workflow, Cyborg compute called the Nova compute called the Cyber API to claim required GPU resources, and then it defines the XML with the GPU PCI address returned by the Cyborg. And if failed in the process of VM exploring, Nova Compute should call the Cyber API to release the related resources. Next is a workflow of the GPU runtime attachment, or called the hot plug. To do so, we use Nova attach command with specific instance ID and accelerator ID and accelerator type. To attach a GPU at a runtime, things are a little different with the boot time attachment. First, Nova API query DB and get the compute node which has the instance. Then it calls the Cyber API to list the accelerator resources and in that compute node. And if there exists the required GPU resources, it will pass request to the compute node. In this phrase, in the phrase of attaching accelerators to the instance, Nova Compute add a new XML with the GPU PCI address. And next is our work on FPGA. We use image properties to define the accelerator type and the FPGA functions to support the request time programming. Also, we use the existing glance table for FPGA bit streams. The workflow difference between the GPU and FPGA is because of the glance involvement. And it's the same in the phrase of resource updating and the instance scheduling. What's different is in the phrase of attaching accelerators to instance. In this phrase, before Nova claim the resources, it should call the Cyborg API to program the FPGA bit streams, and then periodically check the status of the programming. And in Cyber side, Cyber agent should first retrieve the bit stream from glance and then program it to the FPGA VF or PF through the drivers. When the programming is finished, the Cyber agent should update the Cyber DB to change the type of FPGA according to the FPGA functions, which is specified in the image properties. And the reason to change the type of the FPGA VF or PF is that the resources may be different in the hypervisor level to be attached. For example, if the FPGA is programmed with a given smart NIC bit streams, then the cyber should change the type from the FPGA to the smart NIC so that the hypervisor can attach this to this device as the network interface. Well, I finished my part. Now it's the demo part. Zhenghao, it's your turn.
Hello, everyone. Okay, let's start my part. I will finish the rest of the sessions. In section 4, I will show you VM provisioning with GPU pass-through. First, let's look at our environment. This is the topology, and we have 3 nodes, 1 controller and 2 computes. Next, I will show that. Wait. Oh, I'm sorry. Hey, what? No. Could you help me? It's not display.
Move to this screen.
This screen? Yeah.
Sorry, I can't.
You can see it right there.
Okay.
Yes.
Okay, you can see that there are 3 nodes. Node 4 is a controller, and node 5, node 6 are compute nodes. We check the node 6 and find there is a GPU on node 6. And node 5 have no GPU on it. Next, we can check call Cyborg API to check if there is deployable info in Cyborg. Okay, there is no deployable info in Cyborg. And next, I will start Cyborg agent on node 6. let's query again. Okay. Cyborg agent collect the GPU info and report it to Cyborg conductor so we can see the GPU info in Cyborg. Okay, next, we can create an instance with GPU. Before that, we should, oh, I'm sorry. Before create an instance, let me update the image property. I will add a property named hardware accelerator. Oh, I'm sorry. Okay, and check it. Then I will create the instance with the image. Wait, let's wait the state become active. Okay, it worked. And I will log in the guest and check okay, the GPU the guest have the GPU that we checked on node 6. Okay, my demo is finished. In section 5, I will give you a brief summary. Okay, this is our achievements. We use Cyborg to manage different accelerators in Lenovo product and integrate with Nova from a standard workflow, creating them with GPU, FPGA, and so on. The following is future work. You guys can just look at it, such as supporting sharing accelerator. Okay, before Q&A, and thanks Rusher first. Without his patient work, we won't be here to share. And I have finished my part. Does anyone have questions?
Can we add 2 or more GPUs to one VM?
Pardon?
Can you add 2 or more GPUs to one?
Definitely. What you must do is to, in the image properties, you must add some new key and value in the JSON in that hardware accelerator and add the number 2, and you can add the 2 GPU in one VM.
Here?
Next page, 15. Yeah, in the command.
It's for the hot plug attachment for the attach one GPU at once using this command.
Hey, so I was curious in the demo that you just showed, did you have to modify the Nova code itself to make that work?
Yeah.
Were you using the PCI pass-through?
Yeah. We use the PCI pass-through.
We just use the PCI pass-through table.
Okay. All right, thanks.
And we don't use a whitelister, and we don't need to configure the normal configuration file.
Okay. All right, thanks.
Actually, that's a follow-up. On that specific question. So you said you are basically using the PCI pass-through filter. So then, what's the net benefit from using Cyborg for doing VGPA pass-through?
I beg your pardon?
So, sorry about that. My question was more, okay, no, you're using PCI pass-through for attaching GPU to the guest. So my question is not really technical, but more, I would say, use case basis. What is the net benefit of using Cyborg for attaching the GPU compared to the classic VGA pass-through case?
Okay, you mean that how to how to compare the host VGA controller and the 3D controller?
No, I think what he meant is why use Cyborg instead of using the vGPU that already have Open.
No. Yeah, not talking about vGPUs, just talking about classic PCI pass-through. What I wanted to understand is, besides the fact that Cyborg manages its own API for knowing the accelerator resources, from a user point of view, will I see any net benefit, any new possibilities using that specific Cyborg API for that specific use case, or is it just feature parity at the moment?
Well, in my opinion, right, you try to solve a problem where, like, you try to describe all these accelerators with all these kind of properties.
So the GPU is just one of the use case, and you can use the metronome and other the accelerators, not only the hardware but also the software. And Cyborg is going to provide the general management framework.
Okay.
You manage GPU right now, but later on you won't have other stuff. You just don't want to change the workload over and over.
Yeah, it won't change the workflow if whether you add whatever the accelerators you add.
Okay, thank you.
So,
Okay.
any questions?
So you refer to a new command, right? No accelerator attach.
Yeah.
Did you modify libvirt behind the scenes to make the attachment happen? Can you describe that flow?
Actually, I show you in our slide is the workflow, and the implementation details are very different, varies in different kinds of hardware. And if you are using other hardwares, like the QAD card, and you should modify the hypervisor, and because it has some problems to use that in at this moment. And when you use the share mode and other maybe virtualized, I think the hypervisor should first support that.
But as long as PCA pass through, you take the PCA function, put it in an XML snippet, now give that to the domain, right? So that's the bottom line. Whether it's QAT or GPU or whatever it is, ultimately it's a PCI device.
Yeah, but how to use? But there are some, in NFV environment, there are some accelerators which you can't attach to the hypervisor using pass-through.
I see.
Okay, like the compressing and you can we now use the share mode to use the QAD card to do the compressing. So we modify the hypervisor to support the the share to share the accelerators.
Okay. All right. Thank you.
Okay,
Hey,
anyone else?
Okay. Thank you all for your time, and again, I hope you can have good days in Vancouver.
Thank you.